Good morning, good afternoon, and good evening, everyone. Welcome to our OpenFOAM and Combustion Simulation webinar, which is launched by Professor Huangwei Zhang at NUS. And I hope you had a wonderful week in the past. I'm Yiqing Wang from Peking University. Today, it's our pleasure to have Dr. Thorsten Zirwes from Stanford University and the KIT to give us a talk about highly accurate and efficient simulation of combustion on modern supercomputers with OpenFOAM coupled to Cantera. And Thorsten received his PhD in chemical engineering from the Karlsruhe Institute of Technology. He has been using OpenFOAM for 10 years and is a contributor to OpenFOAM and co-author of Cantera. His research concerns the detailed simulation of combustion process with a focus on high-performance computing. He developed several approaches that target performance optimization for large-scale application of OpenFOAM and improve the accuracy of molecular transport models. His solvers and models have been used by more than 25 research groups around the world as well. He received a Best Paper Award at the ESI OpenFOAM Conference and the Golden Spike Award from Germany's National High Performance Computing Centers. And he teaches a biannual one-week OpenFOAM course in Germany and supports OpenFOAM users on the high performance computing cluster at the KIT. He is currently a visiting postdoctoral scholar at Stanford University as a DAAD prime fellow, working on resolved simulation of porous media burners and ammonia combustion. And please raise your question in the chat during the talk. I will read the questions as many as I can as the time allows. And so now let's look forward to Thorsten's interesting talk. And Thorsten, please, and the floor is yours.
Yeah, thank you very much for your kind introduction. Also, thank you for inviting me to this OpenFOAM webinar. I've seen all the previous talks. I learned a lot. So hopefully you feel the same about this talk. So I'm going to talk about a new solver for reacting flow simulations that we implemented in OpenFOAM, which specifically targets the accurate simulation of detailed flames, where we resolve all the flame structure, the internal structure of the flame, and how we make this solver then efficient for large-scale simulations on supercomputers. If you want to do these kinds of detailed simulations, you have certain requirements. So first of all, we need accurate molecular transport models, because if we want to capture the correct inner structure of flames, we need to consider all of the molecular diffusion fluxes of the chemical species. Then these types of detailed simulations demand a lot of computational resources. So we want to make sure that the code runs as efficiently and as fast as possible. And lastly, when we spend that many computational resources, we also want to make sure that our simulations are accurate and we get good results. So in 2012, we started the development of a new OpenFOAM solver that we call EBI-DNS-FOAM at the Engler-Bunte Institute at KIT. And since 2013, I became the lead developer of that code. In the meantime, the code is now shared with many different groups. So more than 20 research groups around the world are using our code. It's also used in industry. And over the past couple of years, some of the developments I've done have also been contributed back to both OpenFOAM and Cantera, which means I'm now listed also as co-author of Cantera and contributor to OpenFOAM. But let's start with the first requirement. How do we get detailed molecular diffusion into our OpenFOAM solver? So if you run any type of reacting flow simulation with the standard OpenFOAM solvers, so for example, reacting foam or row reacting foam, then what you are solving are basically the equations you are seeing here. So here you see the balance equation for the species masses with convection, chemical reactions, and diffusion. And then we have an energy equation here for the total sensible enthalpy. And in the standard OpenFOAM solvers, you will notice that the diffusion coefficient is the same for all the species, which means OpenFOAM employs basically a unity Lewis number approach. And then typically you compute your transport coefficients with a Sutherland model. But for us, this is not sufficient because we want to resolve the whole flame. We want to resolve all the species profiles. So we need detailed molecular diffusive fluxes, which means, first of all, we have to modify these equations. So in our new solver, the equations we are solving look like this. First of all, you can notice that now the diffusion coefficient is different for each species. However, this also has some implications which lead to two additional terms. One term here is the correction velocity. So depending on which diffusion model you choose, commonly you will choose the mixture average diffusion model, which is also known as the Curtis-Hirschfelder approximation. It is not necessarily guaranteed that your diffusive fluxes add up to 0. So then you define a correction velocity, and this correction velocity will take care that all your diffusive fluxes do add up to 0. And also, when all of your chemical species diffuse at different velocities, they have different contributions to the energy equation. So this is why you get the second term here, where we then take into account the different energy carried by the species moving with different diffusion velocities. And then what you want to do is you want to compute all of your transport properties, which means viscosity, heat conductivity, and the diffusion coefficients from detailed models, in our case from kinetic gas theory, which means first of all, you need some accurate mixing rules. So what you see here on the bottom left is the mixing rule to get the mixture average diffusion coefficient for species K based on binary diffusion coefficients. And then the binary diffusion coefficients are, for example, computed like this. And then you have parameters like the sigma here, which is the collision diameter, which is then different for each species. How do we achieve these kinds of detailed simulations of the computations of the diffusion coefficients? This is done by coupling our OpenFOAM solver to Cantera. I think many of you will know Cantera. Cantera is an open source library which already implements all of these detailed models that we can then use to compute the transport coefficients. We follow an idea that first was made by Gescheider and Rehm, who were the first to couple OpenFOAM and Cantera. So the basic idea is, in OpenFOAM, we solve our basic governing equations, which means our total conservation of mass, the conservation of momentum, or Navier-Stokes equations, conservation of energy, which in our case is the total sensible enthalpy, and all of our species mass fractions. And then in Cantera, we compute all of our detailed transport coefficients, as well as thermophysical properties like the heat capacities. And by now, all of the Cantera routines that we need are implemented as its own OpenFOAM thermal library. So if you use our code right now, you don't even have to compile Cantera as an external library. You can directly compile our OpenFOAM thermal class, and everything is included there. Of course, we also want to make sure that our code is correct. So therefore, we have a suite of validation cases. One of the most simple flame setups is a one-dimensional, perfectly premixed, freely propagating flame. The idea of that flame, if you're not familiar with this, is we have a one-dimensional domain. In this case, for example, I computed a methane air mixture with a GRI 3.0 reaction mechanism on a one-dimensional domain, 10 centimeters in length, 10,000 cells. Initially, the left half of the domain is filled with unburned gas. The right side of the domain is filled with the hot burnt gas. And then on the left, you have an inlet where your unburned gas is flowing into the domain. And if the inlet velocity is equal to the laminar flame speed, you will develop a steady state flame inside that domain. And then we can run this simulation in Cantera and also with our OpenFOAM solver and compare, for example, the species profiles inside that flame. So what you see here are the spatial profiles of species mass fractions of the main species computed with Cantera and computed with our EBDNS foam OpenFOAM solver. And of course, you see perfect agreement because now we are using exactly these methods that Cantera provides for us. And also, if we look at intermediate species, then of course, again, we see perfect agreement. Now that we can capture detailed flames. We also want to make sure that the OpenFOAM solver itself runs as efficiently as possible so that we can run very large flame simulation cases. And for those of you who have run flame simulations with finite rate chemistry and a large number of chemical species and chemical reactions, you will know that in these types of simulations, most of your simulation time may be actually spent on computing chemical reaction rates. And so we came up with basically 3 solutions that help us cutting down the simulation time by a lot. And in the following slides, I will go through these 3 steps. The first step is to not use OpenFOAM's own ODE integrators. So what we usually do in these types of flame simulations is we have an operator splitting approach where we do not use the reaction rates directly as source terms for our balance equations, but we first compute an average chemical reaction rate averaged over the CFD time step. And for this, we need ODE integrators. And the ones provided by OpenFOAM, they work, but they are not the most efficient. So therefore, we found that the CVODE integrator by Sundials performs very well and is very stable. Secondly, we want to make sure that the code that is involved in computing the chemical reaction rates is as optimized as possible. In order to achieve this, we employ a method known as automatic code generation. So the idea is we have a tool that reads in a reaction mechanism and then generates highly optimized C++ source code, which is very efficient at computing chemical reaction rates. And the third step we employ is a load balancing approach. So if you run your simulation of tens of thousands of MPI ranks, then some of your parallel processes might be faster, some might be slower. And to avoid processes waiting on slower processes, we also implemented a load balancing approach. So why do we need to take care of the chemical reaction rates? Why do they take so long? As probably most of you know, in reality, even for simple fuels like methane, unfortunately, the chemical reaction is not as simple as this. In reality, it looks more like this. So here you can see, for example, the GRI reaction mechanism. During the combustion of methane, you have a lot of intermediate chemical species, and these will react with hundreds, depending on your mechanism and case, maybe thousands of chemical reactions. And this, of course, is expensive. It's not only expensive because we have a large number of chemical reactions, it's also expensive because some of those reactions are very fast. And in general, as I said before, you don't want to use these reaction rates directly as source terms for your balancing equations, because then you have to run your simulation at the time step of the fastest chemical reactions. Instead, what we do is we use operator splitting. So if we want to use our chemical reaction rates omega for species K, which is defined as the change in time of the species concentrations, what we do is we first assume that every cell in our computational domain is a closed batch reactor. So we completely ignore convection and diffusion, and then we can reduce our equations to a set of ordinary differential equations, ODEs. And then we just integrate our reaction rates over the CFD time step dt. And then again, we need an ODE integrator, which takes many small time steps for the chemistry integration over one time step in the CFD simulation. And then what we have is our species concentration at the beginning of the CFD time step, the species concentration at the end of the ODE integration. And with this, we get an averaged reaction rate over the time step. And again, this is very time consuming. So in general, you want to use very fast ODE integrators, for which we use here CVODE by Sundials. Now that we are using a very good ODE integrator in our new OpenFOAM solver, we can then do some more profiling of the performance of the code. So even though we are now using a good ODE integrator, we still might spend more than half of the total simulation time on computing chemical reaction rates. And what I'm going to show you next is profiling of the performance of our code using the GRI 3.0 reaction mechanism with the tool perf, which is a very simple profiling tool, which is part of the Linux tool set. And what you see here in this line is that we actually spend 20% of our whole OpenFOAM simulation on evaluating the exponential function. And of course, this is a lot. So we want to reduce the time spent in the exponential function. Why do we need to evaluate that? Because of the chemistry, of course. One big part is the Arrhenius law. So for each of our, let's say, hundreds of reactions, we need to compute our rate constants k. And if they follow Arrhenius law, then we have to compute the exponential function of the activation energy by the universal gas constant time the temperature. Now, what's the concept of optimizing the computation of chemical reaction rates without losing any accuracy in our results? The general idea is the following. In most CFD tools, like OpenFOAM, the way you compute chemical reaction rates is by providing, first of all, a text file, your reaction mechanism file, which contains all of the parameters, let's say the Arrhenius parameters, for all of the chemical reactions. For Cantera, it might be an XML file. For Chemkin, it might be a dot input file. But in general, it's some kind of text file. When you run your simulation, your CFD tool, let's say OpenFOAM, reads in this text file, and then on the fly will construct the different types of reactions and will then compute the chemical reactions based on that information. What we want to do is we do not want to use a general implementation that works with any type of reaction mechanism. We want to use for every different reaction mechanism a different type of library which contains highly optimized source code, which is specialized on computing the reaction rates for that one reaction mechanism. Therefore, I created a tool which basically reads in the text file, or the XML file in this case, of the reaction mechanism containing all the data for all the chemical reactions. And then it performs some optimization steps. The first step is to reorder the chemical reactions and species in the reaction mechanism. And we do that to utilize some of the high performance capabilities of modern CPUs. Then the tool eliminates redundant operations. So if you remember in the Arrhenius law, you have the exponential term. But if you have a reaction where the activation energy is 0, then you're basically computing exponential function of 0, which is 1, which you don't really have to compute. So the tool scans for any type of those redundant operation and just eliminates them completely. And then the tool generates the C++ code to specifically compute reaction rates for one reaction mechanism. And if you compile that C++ code, it will then generate an OpenFOAM library, which you can directly use to compute the chemical reaction rates. Let's make an example. So I won't go too much into details, but this would be here an example for the XML file, the text file containing the reactions for the GRI reaction mechanism. This here would be, for example, the section for reaction number 316. And then here you find the 3 coefficients for Arrhenius law, A, B, and the activation energy. And now my converter tool reads in this reaction mechanism, does some operations like reordering reactions and species, eliminating redundant operations, and then it generates this C++ code. And what you see here, for example, is you see a long list for all the values of A, B, and the activation energy divided by the gas constant for all the reactions in the GRI mechanism. For those of you who are interested in details, I will quickly show you some of the types of optimizations that are performed when generating the source code. At the top, you see some compiler-specific instructions. So if you want to have code that is as fast as possible, you cannot use just standard C++. You have to use some compiler-specific features. And then here, for example, for the GCC compiler, we use some specific intrinsics of that compiler. A very important aspect is the way you store all the data. So during the computation of the chemical reaction rates, we want to make sure that all the data we access is stored linearly in memory. This avoids things like cache misses and will speed up your code by a lot. Then, of course, since we are generating this code for one specific reaction mechanism, all of the variables, like for example, the number of reactions, the number of species, are known to the compiler at compile time. So the compiler can make much better decisions on other optimizations like loop unrolling. Then here, for example, you can see the loop that computes the rate constants from the Arrhenius equation. And here you can see why it is important to reorder reactions. So generally, in your reaction mechanism, you have different types of reactions. You may have plain Arrhenius reactions, fall-off reactions, P-log reactions. And what you want to do is to group similar reactions into one loop, because this enables you to access vectorization on modern CPUs. In case you don't know, vectorization basically means in the same time you can do one floating point operation, let's say a multiplication. You can actually do 4 or 8 multiplications. However, this is only possible if all of the data is laid out in a very specific way, if your loops are written in a very specific way. And of course, our tool takes care of that. And lastly, you might have seen that this loop only goes over 228 reactions. But the GI mechanism contains well over 300 reactions. And the reason is, as it turns out, in the GI reaction mechanisms, more than, or pretty much exactly 100 reactions have an activation energy of 0. So we don't even have to evaluate the exponential function for these reactions. We only do this for those reactions that we actually need. Of course, writing a fast code is easy. Correct and accurate is not that easy. So we also have some validation cases for that. The most simple validation case to just test the chemical reactions is autoignition, in this case for methane and air. This is a 0-dimensional setup, so you have no contribution of convection and diffusion, just homogeneous, perfectly premixed chemical reactions going on. Here we start with a temperature above the autoignition temperature, with a methane-air mixture, with some hydrogen to speed up the simulation. Again, we can run the simulation in Cantera, and also with our new solver, EBI-DNS-FOAM in OpenFOAM. And again, we see perfect agreement of all the species mass fraction over time as the flame undergoes autoignition. And of course, the same is also true for all of the intermediate species profiles. Now, do we get a speed up compared to the standard reacting foam OpenFOAM solvers? What you see here is the time it takes to compute chemical reaction rates for the autoignition case from the previous slide, computed with the standard reacting foam solver. And here I ran the simulation with 3 different ODE solvers, Rodas, Rosenbrock, and SolX, provided by OpenFOAM. And it takes about 0.02 seconds, just the time computing the chemical reaction rates. If I run the same simulation with our EBI DNS-FOAM solver, using CVODE as ODE integrator, and using the automatically generated source code, we get about a 20x speed up for the computation of the chemical reaction rates. And again, very important, we get the same results within ODE solver tolerances, because we didn't do any modeling assumptions or simplifications. We just laid out the code in a way that is more efficient to execute, basically. The last thing we need to do is to take care of load balancing. Why is this an issue? Imagine you want to simulate a Bunsen flame. And here you see a hydrogen or a methane Bunsen flame that I did in OpenFOAM. And let's say you run this case in parallel. Then you split this computational domain into subdomains. And you already know, if you perform operator splitting, you will do many time steps for the chemistry within one CFD time step. But you will take more time steps if locally the chemical timescales are very fast. So of course, if you look at domain 0, there's no flame at all. So the ODE integrator doesn't have to do much work. Whereas in domain 1, there's a flame, very high reaction rates, and you have to take a lot more internal chemical time steps to get the average reaction rates. What you could do, for example, is to distribute the mesh differently. So you might have more cells in domain 0 than cells in domain 1. But of course, if the flame moves, or you have a turbulent flame, you will not know where the flame will end up. So statically doing the load balancing in practice doesn't work that well. So in general, you want to have some type of adaptive load balancing. Then, in order to find out how bad these load balancing issues are, I did some profiling on the MPI communication in OpenFOAM. Let me explain to you what you see here. So you see the same flame simulation of that Bunsen flame you saw on the last slide, but now run with 120 MPI ranks. And each line you see is one MPI rank, and the x-axis is time. And here we see one time step of the simulation. Blue means time spent in MPI routines. Black means useful computations. So in general, we want to reduce the amount of time spent in the blue regions as much as possible. What do we see here? So here, for example, this is all the MPI communication related to the pressure correction loop in OpenFOAM. Here we see all the MPI communication during the solution of the conservation of chemical species. Here we see the conservation of energy. And then here we have some the time spent on computing the temperature from enthalpy and also computing the thermochemical properties and transport properties. So all of these thermo and transport computations, they are just local. They don't require any MPI communication. So on the right side, you don't see any blue parts. What I'm interested in here is this part. So this part of the simulation time step is the computation of the chemical reaction rates with the GRI mechanism. And you see, first of all, this part, computing the chemical reaction rates, takes about half of the whole time step. And what you also see is that a lot of this time is spent in blue regions, which means it's spent waiting, basically. So all of these different processes here, they finish computing the reaction rates at this point. And then for all of this time, they spend waiting on the slowest process. And if you look, for example, at this process here takes all of this time to compute the chemical reaction rates. It might be that there's some local reignition going on, or for some reason, very low timescales or very fast timescales. So all of the other processes have to wait for this one process. Therefore, I came up with a relatively simple implementation to tackle the load balancing issues, where we take into account that the slowest process limits the overall performance. So here you see the time spent on each of the MPI ranks used to compute the chemical reaction rates, now sorted. So this is the slowest process, which takes a lot longer than all of the other processes. And the setup I came up with is basically, first you measure the time it takes on all of the processes for computing the chemical reaction rates. So let's say here, process 0 takes 12 seconds, process 1 takes 9 seconds, and so on, to compute the chemical reaction rates. Then once every 100, 1000 time steps or so, you broadcast this information to all processes. So now we have a list on all processes where we know who is the slowest process and who's the fastest process. And then we will form pairs between processes. So the slowest process will form a pair with the fastest process, the second slowest with the second fastest, and so on. And these process pairs will then share their workload. And if we do this, we have now a much better balanced workload for the computation of chemical reaction rates, and therefore quite a cut in total simulation time. You can see that this load balancing is not perfect. So technically, this is not the optimal load balancing strategy. However, if you go to a very large number of processes, 10,000, 50,000 MPI ranks, then only having a pairwise communication is very good, because you want to avoid any type of communication with these large number of MPI ranks. So only having pairwise communication will help your overall scaling of the code. So just to summarize this section, we created a new solver, EBI DNS form, where in typical simulations, we can reduce total simulation times by about 70%. If you run with very large reaction mechanisms, you might have larger savings. And very importantly, without loss of accuracy within your ODE solver tolerances. And we achieved this by switching from the OpenFOAM ODE solvers to Sundial's ODE solvers, by utilizing automated generated code, and by employing a load balancing strategy. Now, we also want to know that our OpenFOAM simulations are numerically accurate. One popular test case to show this is the Taylor-Green vortex, which I'm going to show you in a bit. But first of all, it's important to understand the type of accuracy you can expect in OpenFOAM. So OpenFOAM itself is a finite volume code working on unstructured grids. And OpenFOAM's overall methodology is limited to a second order scheme. However, OpenFOAM does provide some more accurate interpolation schemes. And the most accurate one is the cubic interpolation scheme. Let's say we have two cells in our computational domain. We have the cell centers C and the cell center of the neighbor cell N. And in between, we have a cell phase. XC is the coordinate or the location of the cell center of the left cell. Let's say it's at coordinate 0. And XN is the cell center of the right cell at location 1. And then lambda here is a parameter that shows the relative distance of the cell phase center between the two cell centers. Now, in the cubic interpolation scheme, we want to find an expression for this polynomial. So we need 4 points where we can evaluate this polynomial. 2 points are obvious. So we know our quantity of interest phi in the two cell centers, phi C and phi N. And the two additional information are then given by the gradients of the quantity of interest phi in the two cell centers. And then if you plug these conditions into the polynomial and do some rearranging, you end up with this expression for OpenFOAM's cubic interpolation schemes for getting your quantity of interest from the cell centers to the cell faces. The first part of this expression is treated implicitly. And it's the same expression that you get if you choose OpenFOAM's linear interpolation scheme. Or if you come from the finite difference world, this would be akin to a central difference scheme. And then you have the higher order contribution, which helps to improve your accuracy. But this part is taken explicitly in OpenFOAM. So this means using the cubic scheme will give you less numerical diffusion, better accuracy, but in general, it's less stable. So you should only run this if you can afford low CFL numbers and also good meshes, so close to equidistant meshes. One canonical test case to assess your numerical accuracy is the Taylor-Green vortex. So this is a very simple test case where you start with a prescribed velocity field, and we have an analytic solution that we can compare our numerical accuracy to. In this two-dimensional case, here's what the initial solution looks like. On the left, you can see the initial vorticity field. So you start out with 4 counter-rotating vortices. And on the right, you have the initial component of the x component of the velocity field at the initial condition. We run this with periodic boundaries, typically on a mesh with 64 squared cells, using second-order backward schemes in time. And for these non-reacting cases, I will show you results from OpenFOAM's standard pimple form. And on the next slide, you will see the velocity profiles along the center line here. So here you can see the x component of the velocity field along the center line after 10 dimensionless time steps. In gray in the background, you have the analytic solution. And then if you look here, the green dash dotted line is OpenFOAM's first order upwind scheme. So of course, if you use a first order scheme, you will have a lot of numerical diffusion, and you will not reach the analytic solution. If we zoom in into this part, for example, you see the dashed blue line, which is OpenFOAM's second order linear scheme, which shows some differences to the analytic solution. In orange, you have OpenFOAM's fourth order cubic scheme, which is a lot closer. And then the black dotted line is the Wino scheme, which has been implemented by Jan Gärtler, which is a third-party library, which you can also use to improve the accuracy of OpenFOAM's discretization schemes. Interesting is looking at the convergence order. So here I ran this 2D Taylor-Green vortex case with the cubic interpolation scheme on differently refined meshes. So here on the x-axis, you have the cell size. So towards the left, you get finer meshes. And then on the y-axis, you have the error norms, L1 and L2 error norms. For coarse meshes, we observe a convergence order of pimple form, which corresponds to a second order. But then if you have a very fine solution, you actually approach a fourth order convergence with OpenFOAM. A more interesting test case is the three-dimensional Taylor-Green vortex. So again, we start out with a prescribed velocity field in this 3D box. I ran this again with pimple form on a mesh with 512 cubed cells. And now we don't have an analytic solution to compare with, but there are some spectral DNS solutions that we can use as reference solution. On the left, you can see the initial flow field in terms of an isosurface of the Q criterion. And on the right, you can see an isosurface of the vorticity. So as the simulation starts, the velocity field decays into a kind of pseudo-turbulent flow. And then we can compare our numerical solution to the spectral DNS code. One interesting quantity is the mean dissipation rate epsilon. So the dissipation rate is defined as the change in kinetic energy over time, or equivalently, the volume averaged integral over the strain rate tensor S. And if I again run the simulation with the different discretization schemes available in OpenFOAM, I get this plot. So you see the dissipation rate plotted over time inside that box. The black dashed line is the reference solution from the spectral DNS code. And again, you see the first order upwind scheme is very insufficient to produce the correct results. The purple dashed line is OpenFOAM's second order linear scheme. And again, we see some considerable differences to the reference code, but the fourth order cubic interpolation and also the Wino implementation, they yield results that are very close to the reference solution. So in conclusion, if you want to get results with OpenFOAM that are as accurate as possible, I would recommend you run your simulations with cubic interpolation schemes. In 2019, Professor Thévenot proposed a mini symposium where he proposed a step-by-step benchmark suite to assess the performance of different combustion codes. And this benchmark suite is based on the Taylor-Green vortex. So now we can not only compare the accuracy of OpenFOAM with different discretization schemes, we can also compare the results of OpenFOAM with different codes of groups that have run this benchmark suite. So one of the groups have provided results with NEC 5000, which is a spectral element code, which has 7th to 15th order accuracy in space. We have results from the Dino code, which is a 6th order finite difference code. And we have results from Yale's, for example, which is a 4th order unstructured finite volume code. Again, looking at the dissipation rate of the Taylor-Green vortex in 3D, run with comparable meshes for all of these codes, we can see that OpenFOAM, even though it's technically only overall second order, performs very well compared with the other high fidelity codes. So if we zoom into this part here of the dissipation rate, then we see some deviations from the reference solution by the Yale's 2 code, but all the other codes, including OpenFOAM, get really accurate results. Here's another example. So here we look at the x component of the velocity along the center line in this box at a time or dimensionless time of 12.11. And again, if I zoom into this part here of the velocity field or velocity profile, we can see that all of the high fidelity codes, including OpenFOAM, give really comparable results. Another interesting case is looking at the parallel scaling. So here you see the time it takes per time step for OpenFOAM's pimple form solver, depending on a different number of MPI rings. And the numbers here show the parallel scaling efficiency. So even at 2000 MPI rings, we are still at roughly 100% or ideal scaling. Then if we go to higher MPI rank numbers, we go into a superlinear scaling range. And even at 32,000 MPI rings, we are still approximately perfectly scaling. Now that we also have results from the other high fidelity codes, we can directly compare OpenFOAM's performance against the other high fidelity codes. And of course, these codes are a lot faster, which is expected because some of these codes are explicit, so they do less work per time step. Some of these codes only work on unstructured grids, whereas OpenFOAM always assumes structured meshes, unstructured meshes. So we would expect that OpenFOAM, as time per time step, is a lot slower than these other high fidelity codes. Maybe just as a comment for those of you who want to run large-scale simulations, usually if you want to achieve good scalability, you want to use the linear solvers, which are based on conjugate gradients, especially the pipelined preconditioned conjugate gradient solver, which has been added, I think, in OpenFOAM 2106, which scales very well up to just a couple of thousand cells per MPI rank. Inside this MPI, inside this DNS code benchmark suite is also a reacting case. So one of the test cases is a reacting version of the Taylor-Green vortex, where we start out again with the Taylor-Green vortex velocity field, but then we superimpose here in the center a fuel-rich region, on the outside region with oxidizer. We specify a temperature profile, and then when we run the simulation, the flame here will ignite and then interact with the Taylor-Green vortex velocity field. This part of the benchmark suite is run with the 9 species and 12 reactions. And now I show results with our EBI DNS form solver. So as the simulation starts, we have ignition and then the interaction of the flame with the Taylor-Green vortex velocity field. Here, I ran the case on a mesh with 256 cubed cells. And one of the codes that performed this test case is the CARFS code from KAUST, which is an 8th order finite difference code. And here we look at the maximum temperature inside our box domain over time. And with OpenFOAM, with our solver, we get perfect agreement with the CARFS code. And similarly, for example, if we look at the temperature profile at a certain time along the center line, then again, we see pretty good agreement with this high order code compared with OpenFOAM. Now, when we look at the performance of the reacting Taylor-Green vortex case, then our OpenFOAM solver performs very similarly to all the other high fidelity codes. The reason is simple. In this reacting case, we now spend a lot of time on computing chemical reaction rates, on computing transport coefficients. And since we took a lot of care of making sure that all of these computations are very efficient, now our EBS DNS form solver performance is comparable to all of these high fidelity codes. So to summarize this part, if you want to have high accuracy results in OpenFOAM, I would recommend using the cubic scheme, but be careful, it's less stable. By running some cases from the Taylor-Green vortex benchmark suite and comparing with other high fidelity codes, we have seen pretty good agreement with OpenFOAM. And also we have seen excellent scalability of OpenFOAM, and also in terms of overall performance, good agreement between our solver and the other high fidelity codes. Now I will show you some applications of OpenFOAM with our EBDNS form code. One interesting case are so-called flame figures. So now that we have a code that is able to resolve the internal structure of the flame and also solve for all of the molecular diffusive fluxes, we can perform interesting cases, in this case where we have a lean hydrogen flame in a two-dimensional domain, which propagates here and then develops thermodiffusive instabilities. This was run on a mesh with around 100 million cells. And you can see here all of these interesting structures developing in the flame. Here we can zoom into this. So on the left, you have the temperature field. On the right, you have the heat release rate. And we can see nicely the formation of all of those cells on the flame front, local extinction, and then at the positively curved parts of the flame, the local increase in flame speed that drives these flame fingers. We use this setup to evaluate some of the combustion modeling approaches that are very popular. So here we have a similar case, which is now two-dimensional in spherical coordinates on a mesh with 9,000 by 14,500 cells. You start off with a premixed quiescent gas. You have ignition in the center, a reaction mechanism with 12 species. And then again, we form these instabilities. And here in reference 2, we looked at the implications of these cell formation on flame-led combustion models. Another test case I want to show you, or application case I want to show you, is the Sydney flame. So the Sydney flame is a burner of laboratory scale that creates a partially premixed flame. So the burner works by having an inner pipe where you have pure methane and an outer pipe with pure air. Then there is some length where these two streams can premix. But here we are choosing a length where we have only partial premixing of these two fuel streams, two streams. On the outside, you have a hot burnt gas flow. And then this hot burnt gas ignites this partially premixed airflow. I ran the simulation some time ago on the Hazelhen cluster in Germany, which at that time was the largest supercomputer in Germany, on up to about 30,000 CPU cores. And we generated something between 15 and 20 terabytes of data. And of course, we made sure that the solver scales well, and you see almost ideal scaling up to, let's say, 30,000 CPU cores. How does the flame look like? So here you see we have the inflow of the partially premixed methane airflow. On the outside, you have the hot pilot at chemical equilibrium. And of course, this is a multi-scale problem. We have a very long flame. The flame reaction zone is pretty thin. So in total, we have 200 million hexahedral cells refined towards the shear layer where we have chemical reactions going on, and running this with a cubic scheme in space. If I zoom into this part of the flame, you can see the temperature field. Here in the shear layer, you have the thin zone where the chemical reactions take place. If I zoom into this part, you can see the zoomed in region for the heat release rate. And then here you can see our computational mesh. So here we really made sure to resolve the whole flame front. Of course, you cannot run this whole configuration in a DNS mode. So this is a quasi-DNS mode. The solid lines are the Kolmogorov length, so which is pretty low in the fast, cold core flow, and then becomes pretty high in the reaction zone where you have high temperatures and high viscosity. So we are about a factor 2 or 3 above the Kolmogorov length in the core flow, and then we fully resolve the flame reaction zone. And the dashed lines here show you the volume or the cube root of the volume of our cells, which is a measure of our grid resolution, basically. These are some animations of how the flame looks like. So we have the temperature profile at the top and the heat release rate profile at the bottom. And now, when I zoom into this part of the flame, you can see the following picture. So on the bottom left is the pipe where we have the inner core flow of the partially premixed methane airflow. And then on the 2D cutting plane, you see the temperature field with the hot pilot flow. and also the reaction zone. In the center flow, you see an isosurface of the vorticity, which shows you the nice turbulent structures. And then as the flame ignites in the shear layer, you have an increase in temperature and viscosity. And then, of course, these turbulent structures are destroyed. One good thing about the Sydney flame is that we have a lot of experimental data. So here you can see at different axial positions through the flame, plotted over the radius, the temperature, the Bilger mixture fraction, the mass fraction of O2, and the mass fraction of water. The solid red line shows you the time averaged profiles of the simulation. And then the blue and green circles show you measurements from 2 different measurement campaigns. And the dashed line and the squares are the RMS values. And you can see pretty good agreement. So pretty much everywhere, our simulation prediction is within these measurement campaigns. Similarly, if we look at the measured velocity field, you can see that the time average and also RMS values between our simulation agrees very well with the experiments. Now, having done the simulation, we can do a lot of interesting analysis. I will just show you one quick example. So in order to decide what the local combustion regime is, so meaning, are we locally more like a premix flame or a diffusion flame, we can find different markers. So for example, here we have the flame index, which is computed from the gradient of methane and the gradient of the mass fraction of oxygen. Here, this is the non-dimensional one. And we can also look at this in terms of the angle between the gradients. So if the gradient of O2 and CH4 point in the same direction, then we are probably in a regime which corresponds to a premix flames. And if these gradients are opposed, then we are probably in a regime where we have a diffusion flame. We can also derive other quantities. So from our detailed simulation, we can, for example, derive values for the gradient of the Bilger mixture fraction and the gradient of, let's say, a progress variable. And then with this simulation database, we can assess, for example, how is the angle between these 2 gradients and where do we violate assumptions made in some combustion models. Okay, so I hope I could show you a little bit of how we implemented detailed diffusion in our OpenFOAM solver, how we improved the performance of the simulation, and then give you some ideas of the types of problems that we can tackle with the solver. If you have any questions about the code or want to use the code, you can find my contact info here, and also some more links about the source code itself. And with this, I would like to thank you for your attention.
Okay, thank you, Thorsten. Thank you so much for a very interesting and informative talk. So we are now open for questions. And I received one question from the audience, and from Yude Su. He said, "Hello, Thorsten, and thank you for the exciting presentation. In terms of the load balancing, so do you repartition the computational domain during the simulation? And if yes, what is the frequency?"
Yeah, that's a good question. So we do not touch the mesh at all. Let me explain. So one big advantage of doing load balancing for the chemical reactions is that all of the computation involved there are purely local, which means technically you don't need any type of communication for computing the chemical reaction rates. And this enables us to share the workload between any 2 processes. So these 2 processes, they don't need to be neighboring processes or having some part of the neighboring mesh. If you do load balancing in terms of mesh repartitioning, this is a lot more expensive. So you need to take care that if you split the mesh in a different way, that you take care of all the shared phases between the processes. And this is usually pretty expensive for the gain that you get. So since we're spending most of the time in computing chemical reaction rates anyways, just doing the load balancing for the chemical reaction rates is enough for us. However, our load balancing approach is completely compatible with any additional type of load balancing. So you can run both repartitioning load balancing and our load balancing for the chemical reactions.
Okay, thank you, sir. And another question is raised by Professor Zhang Huangwei, and he says, thank you very much for the nice talk. So when you rebalance the chemistry loading among different processors, what kind of criteria is used to determine the allocation?
So when we do the load balancing, we do not care at all about any type of spatial information. We just look at the time that each process takes, and then we just form the pairs between the slowest and fastest. So for our load balancing, we do not take into account any type of spatial information.
Okay, thank you. And now Professor Zhi Chen has raised his hand to ask a question, so please.
Okay, thank you very much, Thorsten. I thought I would just ask myself. I was being lazy, didn't want to type. It's very, very nice talk. I've learned a lot. In fact, we have quite a lot of interest in common. So I have a few detailed questions actually. Regarding your Cantera speed up, I think you've just explained partly in your previous question. So did you have to do much to the Cantera source code to have the speed up, or was it just a rearrange of the reactions? So basically, my question is how much of rearrange for the code is needed? Because if there is a lot, then it's difficult to get upgraded with newer versions of Cantera.
Yeah, so right now you can use Cantera in our code either for computing the diffusion coefficients and the reaction rates, or you use the approach of having the automated generated C++ code for the reaction rates. Then you use Cantera only for computing the thermochemical and transport coefficients. The vast speed up you get is by using the optimized source code for the chemical reaction rates. However, we made some changes to Cantera. So in the first versions, when we use Cantera as an external library, you always have to have some kind of interface to exchange data from the OpenFOAM solver, like temperature, species, mass fractions, and so on, and then get back the results from Cantera. Now that we took all of the routines we need in Cantera into the OpenFOAM thermal library directly, we do not have an interface anymore. So we directly get all the information from Cantera. You are correct in terms of updating. This is a bit less flexible now. However, I mean, since I'm the lead developer, I'm usually following all the updates to Cantera. And if there's a change that affects our code, I will just put it into the Cantera part in our code.
Okay, great. So that means you don't need to link the shared library of Cantera anymore in your code.
Yes, so you do not install Cantera at all. It's just all part of our thermochemical library in OpenFOAM.
Okay, that's great. I have another question regarding the Taylor Green vortex. I've been doing that case myself, actually using both OpenFOAM and the higher order finite difference code. I actually observed some differences when comparing a density-based solver, in that case, the density of the finite difference code, and a pressure-based solver in OpenFOAM. Did you see any difference in that sense when you compared your results to CAFs, for example?
Yes, so we have submitted a paper which goes into very fine detail about the comparison to other high fidelity codes. Unfortunately, the paper is stuck in review for quite some time, so I hope it will be published soon. What we see is, if we compare results of the incompressible Taylor Green vortex with low Mach codes like Dino, NEC 5000, we get excellent agreement. If we run the reacting Taylor wheel vortex case, then there start to be some differences between the low Mach number codes and the fully compressible codes. OpenFOAM, even though it's technically not fully compressible, I mean, you have the full coupling between density and temperature and so on, but OpenFOAM tends to agree better with the fully compressible codes. That's why I showed the comparison with cars. If we compare our reacting results with, let's say, Dino or NEC 5000, you see some differences. And we believe this is based on the fully compressible versus low Mach application.
Okay, I see. Great, that's fantastic. Just a few comments in the end, because I was working on the Flem index and the cross dissipation rate stuff for quite a while. It was very, very encouraging to see in your very resolved simulations that the gradient of mixture fraction and focus variable, they align, which means the cross dissipation can be ignored, as we have done already. Okay, yeah, that's just a comment. Okay, thank you very much.
Okay, so let's go to the next question. And here's a question from Dr. Shangpeng Li. And he says, hi, thank you very much for the excellent presentation. I would like to know how much of the 20 times speed up of the chemical computation comes from using some dear ODE integrator, or how much comes from the generalized C++ code?
Yeah, so unfortunately, I cannot answer that question because basically when I implemented this, I did both things at the same time.
Okay.
Generally, I can tell you that the speed up that you get by using sundials over the OpenFOAM solvers very much depends on the tolerances for the ODE solver. So generally, the tighter your ODE tolerances, the faster sundials will be compared to the OpenFOAM solvers. And for these types of DNS or quasi-DNS type simulation, you generally want to use pretty tight tolerances. So this is where the sundials solver really shines, even though technically it is not the most efficient approach. But since the folks at sundials have a lot of experiences and a lot of time spent on optimizing the code, in the end, we found that this performs the best for us.
Okay. And another question is from Professor Boson Wang, and he says, hi, Thorsten, glad to see you here. I still remember your talk in HLRS 2017. You mean the speed up of your optimized ODE solver about more than 20 times than OpenFOAM ODE solvers. Afterwards, you mentioned 70% faster. What are the correlation of both numbers? Is your ODE optimization still be compatible with ISAT? And if 30 faster is achieved at last for 3D parallel simulation, load balancing or ODE optimization contribute more?
Yeah, so the 20 times speed up is only looking at the time it takes to compute chemical reaction rates. So this will, of course, only be some part of the overall simulation time. The 70% is with respect to the overall simulation time. Of course, it's very hard to give very general numbers. This all depends on the size of your reaction mechanism, the tolerances of your ODE solver, the time step of your simulation, the type of programs you have, and so on. In general, our approach is technically possible to with ISAT, although in the form it is implemented right now, it is not compatible with OpenFOAM's ISAT. So there you had to do some form of re-implementation or at least adaptation of the code. But in theory, there's nothing stopping you from combining this further with an ISAT approach.
Okay, so you just answer another question raised by Kun Wu. He asked about do the ISAT and the DAC algorithm in OpenFOAM still work in the EBI-DNS form?
Yeah, so again, right now, in the way it's implemented, it is not compatible with ISAT in OpenFOAM. One of the problems is because there's not one OpenFOAM. And by now, the ISET implementation in the OpenFOAM.com version is different to the OpenFOAM.org version. And keeping up with that is pretty painful. So at some point, we decided to drop support in that. Of course, it's always possible to implement this yourself, but this would be some dedicated implementation. But now it's relatively easy to update our code to different OpenFOAM versions because we are not too tightly locked into their chemistry structure.
Okay. So another question from Professor Zhang Huangwei. He asked, for the spherical flames, did you use adaptive mesh refinement to capture the flame front?
No, since these simulations were in 2D, it's not that difficult to have good resolution throughout the whole domain. So this was done with static mesh.
Okay, so and another question is it possible to use load balancing in your code with Lagrangian approach or just Aurorian approach?
Yeah, so the load balancing is completely independent to everything else. So you can combine it with different types of load balancing. You can combine this with Lagrangian particle tracking. You can combine this technically also with multi-phase modeling or conjugate heat transfer. But this is a completely separate part of the code that does not affect other types of simulation you can run in OpenFOAM.
Okay. Another question from Dong1, and he asks, he says, thanks for your talk. Your simulation time is at nanoseconds, and the results compare well with the experiment result. So is the measurement in experiments also at a nanosecond time scale?
I cannot tell you this from the top of my head. I would have to check the paper. Oh. But while we are running pretty small time steps, the experiments do a lot longer times in general to average their results. So I guess the total amount of measurements, I mean, we have more data points from the simulation than in the experiments, but both data sets seems to be well converged.
Okay. And okay, so Professor Zheng Chen would like to ask a question by himself, so please.
Nice to see you. Thank you for your very nice talk. I have a question about spherical frame. As you mentioned that it's two-dimensional, you should very fine structures. I remember a few years ago, actually, you did some simulation for 3D expanding frames. You'll see this kind of very interesting cellular structure. Do you think the 2D simulation for hydrogen air agrees with your 3D results in terms of the cellular structure?
No, it does not. So of course, if you run this in 3 dimensions, you will have another dimension that will take part in the curvature of the flame, which can be pretty extreme at the flame cusps. So you will probably tend to more extreme curvature values, which means a wider range of local equivalence ratios and also local flame speeds. But of course, running the 2D simulation is a lot faster. So if you want to do some kind of parametric study, this is much more nicer to do than running the full 3D case, even though it's possible.
Yeah, I noticed that in your 2D simulation, the domain is pretty large. The frame radius is very large. It's much larger than experiments, actually.
Yeah, so the animation I've shown you, I can even show you a different animation if I can find this. So this was the animation for a flame at one atmosphere. Let me see if I can find this quickly. For 1 atmosphere, the flame is relatively stable. So you need a large radius until the first cellular instabilities occur. Because before that, the flame is pretty small. You have high flame stretch, which stabilizes the flame. Here, if we go to another flame, which is at 5 atmospheres, the flame is a lot thinner. And therefore, you get a flame that is much more prone to thermodiffusive instabilities. So in this case, the flame can be a lot smaller. So instead of 24 centimeters, this has a radius of, I think, 8 centimeters. So you see the occurrence of these structures a lot earlier.
Okay. So for this case, did you do the simulation only for the half domain or the full domain?
This is half domain.
Yeah, I noticed that there's a strange thing happen up the top and the bottom side. The instability first occurs there.
Yes,
This is
so you
strange.
should not evaluate your flame cells at the boundaries. I agree.
Yeah, we have this kind of difficulty before because this instability should come out at randomly in different places, but it's always start from the boundary. We don't know why.
I mean, this is the reason why I chose to do a half sphere simulation and not a quarter, for example.
Mm-hmm.
So you have a large portion of the flame that is far away from the boundaries.
So if you do a 4-domain simulation, maybe the instability become later. I'm wondering. I don't know.
Right. I mean, another thing you can do, of course, is like in the 2D Cartesian case, to have an initial perturbance in the flame. So here for the spherical case, I start with a perfectly spherical flame. And then the onset of the thermodiffusive instabilities comes basically due to numerical errors by the flame being aligned differently to the mesh and so on. So this is where you get the first instabilities.
Okay. Thank you. Thank you very much. It's a very nice talk.
Thank you.
Okay, here's a question raised by Junjun Guo, and he says, "Hi Thorsten, thank you for your talk. Forgot about the efficiency. Did you compare the accuracy of OpenFOAM's ODE integrators and the Sandia's ODE using the same tolerance?"
Yes, of course. So the numbers I showed you are run with the same ODE tolerances with realistic numbers. I could go up to 100x speed up if I use very fine tolerances, but of course this would not be a fair comparison. So at the usual tolerances, we run our simulations, let's say absolute tolerances of 10 to the minus 10, relative ones of 10 to the minus 7, then these are the numbers we get.
Okay. Okay, so now I don't see any further questions now. So I would like to thank you again on behalf of our audience, and now I will hand over to Professor Zhang Huangwei.
Okay, Thorsten, thank you very much for your very nice talk.
Yeah, thank you.
I think in United States it is very late now. It's
yeah, now we have 1 PM here.
Okay. Hope to see you soon physically.
Yeah, of course.
Yeah. Okay.
Thanks again for inviting me, and maybe we will see each other in person on a conference in some.
Yeah, sure. We learned a lot from your talk. Okay. Hopefully we can collaborate in the future.
Of course, yeah, always.
Okay, thank you. Thank you, everyone. Thank you. Bye-bye.
Bye-bye.
Thank you.
Bye-bye.
Thank you. Thanks, Thorsten.